Bettina Heim, who is the lead developer on Q#, which is this really exciting new quantum programming language by Microsoft that is attempting to, encapsulate a lot of these programming language abstractions that Peter was talking about and enable, people to write interesting quantum programs and do something with them. So as soon as we get the mic set up, I'll let Bettina take it away.
Put this on somewhere like down here, that would be perfect. If you could say something to make sure that.
Yes. Okay. So welcome everybody. Thank you very much. Thank you for the introduction. As mentioned, among other things, I'm responsible for the development of the Q# quantum programming language. And we are working hard to make Peter's ideal world that he mentioned at the beginning of his talk reality, or get a little bit closer to it at the very least. So having heard the first two talks, kind of prompted me to switch the rather neutral title of the Q# quantum programming language to something I hope a little bit more inspired, which is going beyond circuits, or why there's so much interesting things that is harder to capture or harder to really think about if you're very focused on circuits. And I hope to be able to convince you a little bit of why it's interesting to go beyond that, and also that this is what we're trying to accomplish with Q#. So before I dive a little bit deeper into some of the language aspects of Q#, I would like to make a brief detour to instead start with the more important question, I think, of why I think we need Q#, or at least something that I hope Q# will become eventually. So whole field, we're not short in aspirations. There are a lot of interesting problems that we hope to solve. Quantum is hoped to be immensely powerful, and among the things that people claim to look into are climate change and antibiotic resistances and all these things like solving world hunger or things like that. However, currently, we're more in the state similar to this. This is one of the very, very early transistors. And we're at a similar point with quantum, where we're still caring a lot about this one single qubit and getting it really good and making it talk to maybe another qubit, or maybe 5, 10, 20, 50 qubits. And if you look at the historic pictures that looked something like this, when people manually rewired things to get a different computation going, then it looks almost awfully similar to our pictures today from quantum computing. So the question here to me is really, how do we get from this really early stage of computing towards something more like the high-tech data centers that we have in classical computing? So this bridge from this very manual approach where each person kind of thought about an application start to finish to something that leverages fully something that a single human would have a hard time to fully understand, that's what's very interesting to me. So kind of giving the inspiration, quantum computing is a huge field, and we all bring our unique strengths, unique set of skills, insight, ideas, perspectives, and vision. I myself, I'm entirely useless in a lab, so I've had 1 or 2 lab tours, but I'm pretty sure if I touch a qubit, it's no longer going to be a qubit. So in that sense, but I'm very good at thinking about more of the compilation techniques, maybe a little bit programming languages and things like that. And conversely, my colleagues in the lab are maybe a little less interested in that. So as we move to scale this up, it's important that we kind of leverage this shared knowledge. So we need the assets that each one of us brings, and every one of you in the room in particular too, if we really want to solve the world's greatest challenges, as we claim. And to me, this is really exactly what languages, and also programming languages, of course, are about. They're meant to kind of bridge the gaps and allow us to share knowledge and leverage this collective knowledge. So I'm going to call it classical computing, or kind of computing on CPUs, not GPUs or FPGAs. If you think about that, it has undergone sort of like a little bit of an industrialization in a sense. We've gone from this kind of mom and pop shop, basically, where you could go to the junkyard, pick out some things, build your computer, do something with it, and you know, build a company from scratch, to something a lot more structured, where people have their field of expertise, have really, really deep knowledge in a particular area, and a lot of different inputs ultimately play together to make it work. So we've built kind of layers and layers of abstraction. So in that sense, to me, this feels like an industrialization in a sense, where we ended up with factories and people building machines that ultimately produce the product. And to me, if we're talking about making quantum computing successful, it seems like a slightly silly idea to think that all that we need is just kind of this more powerful chip. Because this chip is fundamentally different than anything that we have today. So to really leverage it, we will need to undergo kind of the same evolution. I would hence like to take a step back and think a little bit about the abstraction layers in quantum computing that we might be dealing with and what sort of things might come up. Let's structure this a little bit into going down from this abstract notion from a virtual level of memory. I'm going to be very quantum memory focused for a second, to a logical level, to a physical level, and I'm going to omit some lower level things because, as I mentioned, that's really not my strength. If you're starting at the virtual level, it kind of looks a little bit, or to me, it always feels like a game of Tetris. You kind of want to figure out what chunks of work you want to do and how these chunks are really shaped. And there, as in any other programming language, a couple of interesting aspects like space-time trade-offs that are also very common in classical. We have this early work, for example, to decompose a multi-control NOT gate into a sequence of tuffles, and I'm sure most of you know there's also the option to add a couple of more of these tuffles at the benefit of not having to rely on the state of these helper qubits, so to speak. So this is exactly one of these trade-offs where we can trade time at the benefit of saving space. There are other things that are quite interesting in quantum and maybe a little less straightforward. It's very common to base part of the compilation on dependencies to exactly figure out which blocks and chunks need to be executed before other things may run. And in quantum, things are more interesting because even if two things touch the same memory, they don't necessarily depend on each other. There are commutation relations, you know that. So even acting on the same things, sometimes you can freely swap them around. Even if you can't formally swap them around, there's still the possibility that if you do, you're just merely trading one error for another. But all of these things, of course, are rather hard to detect automatically. Nonetheless, it seems like relevant information and something to keep in mind when we're talking about designing quantum programming languages, because ultimately, to me, it's about what information do we care about and how can we represent and leverage it. Another aspect on this still very high level, virtual level, for example, is also rotation synthesis. In most systems, I believe, we won't have native rotations, and even if we do, it's reasonable to assume that there will be a certain finite precision to which we can actually execute these things. If we have control over what precision we actually need, then that might also allow for huge saving in the sense that you can be precise when it matters and be less precise when it doesn't matter, similar to using data types that have less precision. Then on the other hand, of course, there's always the possibility to do that manually. So I've had colleagues spend a year having these huge algorithms and work out by hand exactly which pieces to assign which precision. There's, of course, a possibility to have kind of tools, run a couple of benchmarks, and then sort of figure out what the right numbers are. The reason that I think it is rather a good idea to want to automate this is precisely because people designing quantum algorithms usually design sub-pieces of your end-to-end application. Again, we have different people with different domain knowledge, and a lot of different domains are likely ultimately going to contribute to one application. So it seems like a good idea that we could get from this having to know literally your input values in order to get an optimized version of your program, to being able to convey the knowledge that each domain expert has about a sub-piece of the algorithm, and having an automated way of combining that knowledge to optimize the end-to-end application. Now, this is precisely why I think that kind of automation is relevant not just for large-scale devices, but even for NISC, even early on. Because even if the applications we're talking about are around 50 qubits, if we talk about wanting to look at a couple of hundred or thousands of applications, that's still quite significant work to do by hand. Whereas we should really be leveraging the classical compute powers that we have today to better understand how quantum really translates. So the bottom line for me with precision, or the interesting piece when it comes to languages, is that even what looks like the exact same instruction in your language, in your code, may not actually be translated to the same thing. So this is this kind of context-dependent translation that we would want to do. Going back to our mapping virtual, logical, physical, and whatever else comes after that, we've talked a little bit about allocations, deallocations, about dependency models, and some precision requirements. Of course, as we move from logical to physical, there's always this big, huge, ominous field of error correction that everybody, especially initially, was very worried about. Because qubits are kind of particular. I'll call it the curse of Schrödinger's cat. We kind of don't want to look at it because there's a risk that it dies. And for error correction, people thought that would make it a lot easier. A lot harder, sorry. Luckily for us, error correction still sort of works in the same way, in that we just want to encode information redundantly and use that redundancy to make information resilient to some sort of noise. However, one thing to be aware of is that there's also a lot that has to work together. We kind of need to be able to decode. Usually error correcting codes are good in some things, but not in other things. There's not this one perfect solution really that seems to work for everything so far. So there may be significant classical processing involved in making this work. And here too, we have some interesting trade-offs. If we think about magic state distillation, for example, then there are different codes that we could choose that produce more or less T-gates, take more or less space or time, and things like that. So here too, there's a lot of flexibility. In addition to thinking about these error correction schemes, what you usually also kind of want to know at the physical level is roughly how the geometry of our device looks like. Maybe there are pieces that are particularly reliable or not reliable. If we can actually execute an instruction at the same time on each qubit or things like that, or maybe we can only execute X gates at the same time. So there are all of these things that come into that at that level. And then going lower, this classical quantum coordination that we have, thankfully, an entire session on is one of the most interesting pieces. Quantum algorithms or applications, as we think about them from the theoretical side, almost all involve a somewhat more or less complex interplay between classical and quantum. And to me, it is to be expected as we get to tackling more and more optimization problems that this will become increasingly relevant. So I'd assume that we would have something like a runtime environment that actually coordinates kind of what happens on a quantum processor, what happens simultaneously at the classical processor. We heard concerns about, well, we don't really want to wait for classical processing to finish. That seems like a rather bad idea. So ideally, we want to coordinate that in a way to take optimal advantage of our quantum device. And then, in addition to that, what we need to consider, of course, are things like latency. So one of the things that I think is very problematic with being focused on object, for example, is that it's not really entirely clear to me at this point where these objects even live, because what kind of memories I have at very low temperatures, how much of that is not fully clear, how that will look like in the future. And also, when you do computing, the closer you are to your qubits, of course, the more heat you're generating, the more noise we're generating. So from that perspective, we kind of want to do the classical computation that generates heat away from the qubits, but from a latency perspective, that's, of course, a bad idea. So as we go to lower and lower things, there are a lot of other things to keep in mind. And the bottom line to me is that if we want really to make this next step with quantum computing towards solving problems that we can't do with today's hardware, then we need more than this one qubit. We need to leverage the full potential that new hardware can offer us, but also that our very powerful computing devices that we know today offer us, and that we as a human may have some unique advantages over it, and combine these three aspects. So some of these things that I've talked about here, the conclusion for me here is that automation really is key to getting these things to work together. And this is precisely where we've made, hopefully, a first step with Q#. This is kind of the direction that we're looking at to drive Q# towards. So I'd like to dive a little bit more into detail as to what we have today. We're still preview, so this is a very, very young language. But hopefully it should become apparent kind of where some of the strength may be. From the type perspective, we have, of course, all the simple data types like integers and doubles and biggins. We give qubits sort of their own type. It's not a linear type. It's a data type like anything else. So in that sense, in that regard, we have a little bit less options for verification at the benefit of making it a lot more usable, a lot of quantum algorithms, kind of like slicing, like reshuffling qubits and things like that. It's a convenience thing that we actually allow to do that. All of our data types, however, and here's where we're very different, for example, than C#, are immutable. So everything is a value type, including arrays. Our arrays are all immutable. I'll mention a little bit about what the advantages of that is. We also have operations and functions. We make the distinction between functions that are purely deterministic and operations that may include quantum operations, meaning if you call an operation more than once, you're not guaranteed to get the same output if it gives. Whereas if you call a function with the same input, you're guaranteed at this point to get the same output. And then we also allow type parameterizations of callables. It's currently somewhat not quite as lifted into the type system as it should be. As I said, there's still preview. We're still working on some of the aspects. This chew is a user convenience feature opposed to something that is very relevant for optimization purposes. So what this allows us to do, on one hand, we do local type inference, but we don't do at this point a global type inference. For practical reasons, it just hasn't been implemented so far. The nice thing, however, is that we don't have any kind of mutability across operation boundaries. And this is very useful and comes in very useful and allows us to give exactly certain guarantees that would otherwise be pretty tricky. For example, also related to emulation. For the sake of executing things on the classical hardware to kind of get a better understanding of your quantum algorithm, it's sometimes useful to do tricks that you can only do if you actually simulate your system opposed to if you run on quantum hardware. The way that Q# is set up, we can actually give guarantees that these things that we allow you to do would behave the same way that an ideal quantum system would behave. We do, as I mentioned, distinguish between operations and functions, which possibly could allow us to be a little bit more permissive and kind of encapsulate some of the classical logic while still be aware of it. So in terms of how long does it take to compute and things like that, and what the possible outcomes might be, it just gives us more knowledge. You could achieve that, of course, by embedding into another language. The challenge with embedding in a very mature, large and popular classical language is always that you have to dig through the entirety of that language and make sense of it to, use and leverage that information. For that reason, it's easier for us, in a sense, to define precisely what classical things we can deal with and we know about and we're comfortable with, and grow that as we grow the language. And then one thing we also do is that operation types in particular have certain characteristics that we drag through the type system, because the type system is the one easy way, so to speak, to propagate certain information statically. And among that, for example, is whether an operation can be inverted, can be controlled. There's a little bit of information that we infer and try to propagate. So inferred information, in a sense, is things that we could have put into the type system. It's tracked and propagated like a type, but as a user, you can't require it. You can't say, I absolutely want this operation to be self-adjoint, and this code is only valid if I get an operation that is self-adjoint. However, the compiler will track if you have an array, put in a bunch of operations, and all of these is self-adjoint, then the array is going to be an array of self-adjoint operations. And last but not least, we're fully statically typed, or at least that's the idea. So we have full type information at compile time. There are no runtime types, so we allow type parameterizations for callables, operations and functions, but not for types themselves. In terms of program structure, at the top level, we kind of have namespaces. We have operations, functions, and types. that we allow to define U. There's currently no such thing as a global constant because they are basically equivalent to functions taking unit. Since they're deterministic, at this point in time, there's no distinction between the two, really. One important thing that also Peter has highlighted a lot, operations and functions are first-class values for us. You can freely pass them around like any other integer that you might have. As a convenient feature for us, by default, everything is recursive. Downside is we kind of go and find recursion cycles because these have a little bit more overhead with some of the things. And we support specializations, meaning there's the mechanism, there's sometimes a benefit to making an association between different transformations. For example, a unitary quantum transformation and its adjoint. Obviously, there's a benefit to the compiler knowing about that, and you can kind of try to get an operation and its adjoint one after another and just kick them out and not bother applying them at all. So these specializations, as we call it, are, for example, exactly what is the transformation, what is its inverse, what is its controlled version, and so on. We might consider adding more in the future. Right now, it's mostly kind of being adjoint and controlled. And the nice thing is we, in particular, also auto-generate them. So the compiler will you can, as part of the declaration, you define the type, which includes information about which things should exist. And the compiler, in most cases, is able to just auto-generate these. That, in particular, is also possible independent on what kind of classical control flow you have. For controlled, it's very straightforward, obviously. For adjoint, it's less straightforward. You have variable declarations in between, you have loops in between, possible branching and conditionals. Here too, for a lot of cases, we can auto-generate it. In some cases, if you use particular constructs, will fail, mostly for efficiency reasons. We also allow you as a user to always specify a more optimized version. That here is where we draw the line and don't verify. If you specify your own hand-coded version, at this point we don't do any verification. We take your word that you actually know what you're doing and treat it exactly as what you declared it. Oh, sorry. As I mentioned, we have some statement. The more interesting thing is, of course, we have qubit allocations. These may occur anywhere in the code, so we don't force you to declare them at the beginning and release them at the end. We don't really have data types that are reference type. All of our data types are immutable. However, we allow you to reassign an identifier. And this is really just that. You can reuse the name for something which has nothing to do with its value. We have returns and fails. There's no mechanism for try and catch. We hope to get around not having to deal with the full exception handling. We'll see about that. What we have, what is a little bit out of scope, I think, for most of today's hardware are conditional loops. So loops that don't have a known number of iteration compile time. Usually they'll depend on some measurement results. So they are true runtime dependencies that we can express. Conjugations are pattern of the form UVU dagger. They're mostly relevant for automatic memory management. And the fact that we allow to express arbitrary classical control flow is precisely what I think makes it really interesting, because it's something that we want on one hand from the algorithm's perspective, but now you have the whole arsenal of questions of what can you pre-evaluate, what can you do statically, what makes sense to do, what are true runtime dependencies, and how do you deal with them. That becomes particularly interesting with the coherence times of qubits to make that work. So I think this will be a large project that I hope a lot of research will go into ultimately, and we're kind of setting the first steps in that direction with the language. We allow you to have something like shared scratch space, borrowed qubits. I don't know how many of you know what borrowed qubits is. This is precisely the thing that I mentioned, where you don't rely on your quantum memory being in a certain state, but you're kind of okay with whatever state it's in. The guarantee you give is whatever state you get it in, you'll also return it in that state. And related to that, we basically do some automatic memory management because there's some flexibility, especially in combination with this UV dagger pattern that we allow you to express specifically in the language regarding when you decide to actually do the cleanup. So in classical computing, deallocating memory is as easy as kind of looking at it, cleaning all the data and just marking it as released and you're good. You're just overriding it. With quantum, it can be a little bit trickier because if you just measure it and reset it, you potentially, destroy the computation in another part of your system. So oftentimes what you want to do is really undo the, computation that resulted in the use of that memory. And here is precisely where you can play little games regarding when you execute that and when you maybe don't need to execute that and little things like this. As I also mentioned, the hope is also to get somewhere towards automatic precision management. We're not quite there. This is all work in progress to some degree, but the language at the very least should allow to express you the relevant information as we grow. I won't go too much into detail for the expressions. As you see, aside what makes us a domain-specific language are things like we don't have I/O, we don't have file reads and writes. So in that sense, we're focused, but from the perspective of classical computation versus quantum computation, I think the field is supposed to be pretty much like any other programming language. So just to give a little bit of how this looks like, this, for example, is Grover expressed in Q#. And while there's certainly still a long way to go in terms of this compilation stages that we envision, we hope to get there eventually to a somewhat lower level representation than we have currently. All of that, hopefully, is a lot more interesting to you because I hope most of you by now know we are fully open source. So the full compiler is open source, the full runtime is open source. We're working towards getting something like a language design repository going. It's just been a time problem, but we will be very excited to have people contribute to the language design and have that be an active community and discussion and help us come to a better solution because we're really just looking for the best solution that we can come up with. One thing I wanted to mention, for the people interested more in compilation, we'll also, at the end of the month, release some infrastructure that should make it super easy to plug into our compiler. It basically, who knows what project files are? Make files? Yeah, good. Usually you have some form of reference to packages or other projects or whatnot. With the infrastructure we set up, you can basically have these references, tag them as being references that are to be passed to the Q# compiler. You can prioritize them. They're supposed to implement a certain interface, but they will then be executed as part of the compilation process. You can force them to be executed at certain stages. Right now, as I said, we're still fairly high level in terms of abstractions. As we go to lower levels, we'll keep that infrastructure to make it possible to integrate at any stage during the compilation process. This is all part of a larger chunk, so now my PMs are going to kill me if I don't make a little bit of publicity. My apologies. We've got a lot of open source materials, all the libraries, some chemistry, arithmetics. We've got exercises for those that are not from quantum. We ship a couple of extensions. We have interoperability with Python, so we're leveraging a lot of the .NET infrastructure currently. That's also not necessarily entirely permanent. We'll certainly always offer interoperability with .NET because we're Microsoft and we kind of support that. But we're not to F# or C# or any of these things. We are meant to be a standalone tool and language. Yeah. And useful tools for resource estimation. That is all to say, like, we really hope to gather a community around it and some research around it and make it useful for you. So in short, we're counting on you. Okay, thank you very much.
Okay, we can take a few short questions.
Hi, my name's Thomas Alexander from IBM. You mentioned about classical control flow and associated like arithmetic. There's really almost two types of classical control flow in arithmetic. You're going to have the real-time control flow that's going to be on the order of the lifetimes of the qubits, but then you'll also have offline control flow or like intermediate scale control flow that's classical computations that will take longer than the lifetimes of the qubits. This is likely how a lot of hardware will be implemented in the near term. Do you have a way to differentiate these two within your language? Are you hoping to use like intelligent compilation to get around this?
So from a language perspective, we're not differentiating. However, we're hoping to be able to express enough metadata to basically exactly allow the compiler to take informed decisions. Okay. You know roughly what instructions could be executed in each code block. You know, for example, which of these classical things you could pre-evaluate and things like that. Mm-hmm. So there are games you can play with. Profile-guided optimization in classical computing is a thing. We'll see how much that is possible and makes sense. But I think there are a lot of open, very interesting questions, obviously, as this field grows.
Thank you.
Hi. I guess my question is, what do you think is the next big challenge that Q# has to face?
So part of the challenge, of course, that we have today is that we're trying to bridge really this gap between what quantum algorithms research thinks about and uses and leverages and what current quantum hardware can do. And this is not just number of qubits, obviously. There's a lot, you know, especially related to classical quantum coordination and control flow that current hardware, you know, doesn't yet deal with. We hope to get a better understanding, to leverage Q# to get a better understanding how that can be doable, how hardware needs to be built, how runtime needs to be built on top of that to ensure that it's feasible and to guide that. But the next challenges are certainly really looking to translate it down. We hope to make good progress towards giving at least a spec for a runtime that would be capable of executing all that is expressible in Q#, and at the same time is a little bit more manageable for, you know, hardware platforms to work with.
Hi. Can I just, you mentioned that you had these inferred characteristics of the program. Mm-hmm. It wasn't clear to me what you said, whether this was something that was user-facing that I would be able to use, or if this was something for the compiler to use for itself. Which way was it?
It's something that the compiler uses internally. If you integrate into the compiler, if you write optimizations, then you're able to use those. They're precisely not user-facing because they're usually the way I see it, you can often go one of two ways when it comes to language design. You can either allow people to exactly dictate what to do, or you can give people the tools to give the information and allow the compiler to make decisions based on that. The first option usually would result in some sort of dispatching problem. Say I gave you the option to dictate, I want a self-adjoint operation. And then when it's self-adjoint, I do some optimized implementation here. Then you're likely going to end up with an implementation for your phase estimation algorithm if operation whatever is self-adjoint, if operation is not self-adjoint but adjointable, if it's not, and things like that. So you see, it's kind of what I mean by the dispatching problem then. And then if you don't do the dispatching automatically, we get back towards this. If you really want a performant application, you have to write it start to finish and really say, use exactly this one. And that's what we want to get away from.
Thanks.
All right, let's thank our speaker.